there are four basic interactions of light with matter that we use the photon theory to explain. We can't explain these four phenomena using the wave theory. The first one's a photoelectric effect that we're gonna solve problems with, right? Now keep in mind that the wave theory predicts that light can eject electrons from the surface, but the wave theory would predict that the brightness, not the color, okay, but the brightness of the light should cause the kinetic energy to increase. But the photon theory states that that it's the frequency, right? And this is quite unexpected, right? That light is made of particles, and their energy of those particles is dictated by the frequency and some other constant. But anyway, so that's one of them, right? The next one is Compton scattering. This one's also mysterious, right? A photon bounces off an electron. The electron absorbs some energy, right? So this guy has energy, right? This guy has kinetic energy. This has HF, right? And this is HF naught. Well, if this is some amount of energy, then this has to have less energy. The only way it can have less energy is to have a bigger wavelength or a smaller frequency, right? So bigger, and that's weird, right? Bigger wavelength, smaller frequency, right? You shine light on something and it changes color. The wave model would not predict that. You might predict that the amplitude, that it gets less bright, but you would never predict that the color would change when it bounces off of something. So anyway, that's Compton scattering. The next one is just absorption, but the absorption is very specific. Okay, the photon hits an electron in the orbital. The electron moves to an excited state, and the photon disappears. And it disappears all at once. It doesn't gradually disappear. It's a quantum. Just boom. It just snaps out of existence, right? And the cool thing about absorption is that it occurs only for particular photons. The photon has to have more or less the exact energy needed for this transition, which makes absorption very, very selective. Okay, let me hit the right arrow here. Only with the right energy, right? So if you look, this is an absorption spectrum, okay? Notice that, for example, these, by the way, are emission lines. So when we look at the light given off by excited elements, they give off and absorb energy of the same wavelengths. And that's because these energy levels are what they are, okay? So for example, this guy is this energy level here. This absorption line is this spectral line there. Why some of them don't appear here. I'm not a spectroscopist, I don't know, okay? But what we're seeing here is actually all of the colors of light, basically black body radiation, as seen through the atmosphere of a star. And the star's atmosphere is absorbing particular spectral lines. And by the way, by the particular lines that it absorbs, and by the blurring of these lines by thermal activity, we can determine the temperature and therefore the brightness of the star, which is kind of cool. Okay, so that's absorption, is just the selective absorbing of particular wavelengths of light. We can't really predict that with the wave theory. And then the final one, and this is the most bizarre one, possibly, okay, is that energy just becomes matter. Okay, a photon, if it passes near something massive, typically a nucleus, and the nucleus is needed to balance the conservation of momentum. Energy is conserved and momentum must be conserved. And I think the nucleus carries off some of the original momentum of the photon. But this is really cool, right? The photon just spontaneously spawns a matter particle and an antimatter particle. Now, why it has to create an electron and an electron, this is a regular matter electron, and this is an antimatter electron called a positron. The reason it has to create a matter and an antimatter particle is that electrons are conserved. There's something called conservation of lepton number. You can't just create an electron. You have to create something with a -1 lepton number. We'll learn about that when we get to particle physics. Okay, so we create a matter and antimatter, right? And the cool thing about this is, let's see, the nucleus. Yeah, the nucleus carries away some of the momentum. Oh, I've got some little things. This is an electron, right? Okay, it has a charge of -1. Right, this positron is the same mass as an electron, has a charge of positive, just same charge as a proton, right? But it's an antimatter particle, and then this guy will annihilate and create photons, right? A pair of photons, and you can actually see this when you look at the spectrum analysis radiation, you can see a spike that corresponds to the energy level needed to create an electron. Okay, now let's just keep going here. This is so the question is, right, is light, is it a wave or is it a particle? Well, it's both. I mean, light is something that we can't see directly, right? So we can't expect it to behave like ocean waves or like billiard balls, right? It's some crazy combination of both, right? So basically, light is something that behaves like a particle and like a wave. So how do you know which one it's going to do? It depends on the situation. Okay, you give me the situation and I'll tell you whether it's going to behave like a wave or a particle. But complementarity says that it will never be both. So this is an exclusive or. Exclusive or is only true when one is true and the other is false. Okay, so it'll either be wave or particle, but not both. It's not a permissive or, it's an exclusive or. Okay, so let's just look at this, right? If you shine light into water, it's going to act like a wave. It'll refract. We can use the wave model. If you shine it light, monochromatic light, coherent light on two slits, it'll interfere. This is something that only waves can do. Particles can't do that. Or can they? They can only do it when they act like waves, right? Waves, when they hit some aperture like this, they spread out. This is diffraction. Only waves do that. Light does that. When you shine light on an aperture, it acts like a wave. Okay. If you shine it on a metal, it acts like a particle, specifically with an energy of HF, right? Right. If you shine it on a bunch of electrons, it will reduce its frequency, and it will act like a particle. It will act like a particle when it's absorbed. And it can create matter, which, we don't have a mechanism for waves to do that, but particles can certainly transmute like that. Okay, so yeah, so just to give me the situation, and I'll tell you whether it behaves like a wave or a particle. Here's another thing. I think this will help explain it all. This, I think, is from the New Yorker. We've agreed to count it as both a wave and a particle for tax purposes. Yeah, sorry, I thought that was funny though.